Okay, well, thank you for coming to this talk on using ARM in the cloud. The idea is to save money and to improve your performance. Something else, I honestly just find it kind of cool to be running applications on an entirely different CPU architecture, the same one that you use on your phone or you perhaps use on a Raspberry Pi. Honestly, my motivation around learning more about this was probably more about that than saving a customer's money. So a little bit about me. My name's Andrew May. I'm the cloud lead at Leading Edge. I've been with Leading Edge for, actually 14 years now. And I've got about 7 years of cloud experience, mostly in AWS. Leading Edge is actually an AWS select tier services partner with AWS, and we're based in Columbus. And we specialize in sort of cloud native development, migrations, DevOps, and we're also a sponsor of StirTrek if you want to check out our booth. So what is ARM? Well, originally ARM stood for Advanced RISC Machines, and RISC stands for Reduced Instruction Set Computing. Now these days they say ARM's just a trademark, it's a name, so it doesn't really stand for anything. But that's the basis of it. And this came about with the development of what was called the Acorn Archimedes computer. Now in the US, I don't know that they ever shipped any of these in the US, but I grew up in the UK. When I was a kid in schools, everyone had BBC Micro B computers, and the Archimedes computers were supposed to be the sort of next generation of computers. In terms of performance power, think about somewhere between a Commodore 64 and an Atari ST, somewhere in the middle between those. It didn't set the world on fire. You didn't see a ton of these around outside of schools, but they did develop this new CPU architecture instruction set as part of developing this. Now fast forward a few years, and we've got the original Nokia GSM handset. And they selected an ARM architecture because of its low power characteristics. They could get a long battery life out of this. And they were doing something relatively complex for the day in terms of that sort of handling the mobile signal. Go forward a bit further, we've got the first iPhone. And again, this used an ARM architecture because of those low power characteristics. Now, many of you have got stacks of these at home. I know I have. The various Raspberry Pi devices, different generations, they've all been ARM-based. As the generations have gone on, they've got more advanced, had more CPU cores, and had more power. And then much more recently, Apple's really got into the market of designing their own CPUs. So they're no longer just taking designs that someone else has built and shoving them together as a lot of people like Samsung perhaps have traditionally done. Instead, they're designing high-performance CPU cores that they can use not just in phones and tablets, but they're now powering laptops and desktops. So you can think that ARM's really gone full circle from starting out in these desktops to ending up back in desktops. Okay, so we're not here to talk about desktop computing or phones, we're here to talk about the cloud. So why on earth would they be offering ARM processors in the cloud? One of the big reasons is that lower power consumption. So you get more processing power for less electricity energy. That means you can cram more of these into a smaller space, which is a huge concern for cloud data centers. With the latest generations of processors that AWS is using, they estimate they can get 50% more CPU cores into the same rack space. So that's a big difference in density. Alongside that, there's lower HVAC requirements because cooling is a big deal in data centers. And then they can pass on some of those costs at a lower price, which means they can be more competitive compared to the other cloud platforms. And then they can also tout environmental benefits about this. One of the other benefits they have is these CPU architectures, they can influence their design. So they're designed specifically to run in their cloud data centers, and they don't have to wait on whatever development cycle that Intel or AMD is working on, where they're also trying to produce a processor that works in laptops and desktops and other devices. And I have also heard it mentioned that perhaps they do this because it gives them more leverage against Intel and AMD, because they're still processing a lot of those other CPUs. But if they have a competing device, when they come to price negotiations, this may be a factor. Now, where do we stand currently with the cloud platforms and what they offer? Now, AWS is definitely the leader in this space because they've been offering ARM CPUs in virtual machines since 2018. Now, interestingly, normally you wouldn't have Oracle Cloud on many cloud presentations because they're a fairly niche player, but they were actually the second cloud provider to offer ARM CPUs, starting in 2021. And then just a month ago or so, Azure gave a preview for ARM CPUs in Azure. Now, you try searching about ARM in Azure, you're really going to have fun because it's going to stand for Azure Resource Management or whatever it is, and it's really hard to find details of exactly what they're offering. But it's pretty new to them. Now, in terms of the processors they're using, both Azure and Oracle are using a CPU designed from a third party called Ampere. So they're very similar devices. AWS is a bit different because they're using their own custom silicon from a company they bought, and they're now on their third generation of architectures. And the other big difference with AWS is because they've been doing this for longer, they've started to make use of these CPUs in all their different services and not just virtual machines. So we've got a long list of those, and we'll be talking a bit more about them. Now, Oracle also offers Kubernetes clusters based around ARM CPUs. Now, because AWS has this big lead, a lot of the rest of the talk is going to be kind of focused on those things that AWS features, and also because that's where a lot of my experience lies. But I think because Microsoft has invested so much into the ARM platform in terms of optimizations in .NET, and now they've got this preview of the CPUs, that we're going to see a lot more of this coming out in the other platforms. You'll notice at this point, nothing at all in GCP, but we may see something in the future. Now, AWS Graviton is their implementation. It was developed by a company that they purchased in 2015, and we've gone through these 3 generations. So starting in 2018, we had the original Graviton, and this was really a low-power offering. Perhaps great for running a Bastion host, a small web server, but not very compelling as a replacement for your higher performance instance types. Now, it only had 16 cores, and that's a big deal because when they're running that in a data center and they're splitting that up into a number of different virtual machines, they can only get perhaps 8 different virtual machines out of that one physical device. But then fast forward to Graviton 2, and we're up to 64 cores, and that's much more comparable to what Intel and AMD are offering in the data center. And additionally, this is now a much newer CPU architecture. So it's gone from something that was really designed for phones to something that has been designed much for the data center. And actually, it's very much the same CPU architecture that's used in Azure and Oracle Cloud. And they started offering multiple instance types so you could get different balances of CPU and memory and other features. And then they started rolling it into different types of services. And finally, last year, they announced Graviton 3. It's similar, it's 64 cores, it's got faster memory, and they reckon it's about 25% faster than Graviton 2. So there's continual advancement here. Now, in terms of benefits, they're touting that it's about 40% faster than the equivalent Intel CPUs, and this is based upon Graviton 2, and they sell it for about 20% less. So that can give you some big benefits in terms of a large server fleet. One of the interesting features of here is, and I really never thought about this before, is when you get a 2 virtual CPU Intel machine, you're getting 1 physical CPU core that runs 2 threads. And that's because of a feature called hyperthreading or simultaneous multi-threading. Now that's great most of the time, and it gives you similar performance to two cores, but there are times those two threads conflict with each other and it can't do the same amount of work, and there are instances where you're actually recommended to disable that. So you rent a 16 vCPU machine, turn off hyperthreading, and you actually have 8 CPUs. Now because each CPU core is a full core, it also means that they can now offer single core machines, virtual machines, which you'll notice generally in the cloud platforms, you tend to be limited to powers of 2, and it's because they can't really split one of those hyperthreading cores because they can't safely sort of keep those two threads completely isolated from each other. So that means they can offer single core instances at half the price they would have offered for one of those two core instances. So there's additional savings you can have. And again, that's great for low-powered Bastion hosts, web servers, and things like that. Brief pricing comparison, not very interesting, but just really proving out that 20% saving. Something to note, though, in AWS, they already offer AMD CPUs that are typically about 10% cheaper than Intel. So this is only another 10% or so cheaper than those AMD instances. Now, I mentioned a bunch of different services are getting support for Graviton. Perhaps the most interesting of these is Lambda functions. This is your main building block of serverless applications. Those can now run on a ARM architecture, and you can easily just switch in the console between x86, 64, and ARM and go off as long as your code is compatible with that. So it can be the easiest thing to really switch over at an application level. And then there's things like databases, caches, Elasticsearch, now rebranded as OpenSearch for reasons, code build, because sometimes you actually need to build the code that you're going to be running on the architecture you're going to be running it. In terms of operating systems, here we're really looking at Linux with a side flavor of BSD. In AWS, at least, they're not offering Windows, even though there are ARM versions of Windows available. That may be something that becomes available in Azure. We'll have to see. In terms of things that are easiest to switch, really, if you're interacting with an API, you don't care about the architecture that that service is running on behind the scenes. So if you're using a MySQL database, you're interacting with that MySQL API with your driver. And if the architecture behind the scenes changes, as long as the performance is still good, it doesn't matter. Same with caches, something perhaps you're using a REST API, OpenSearch. The only gotcha here is that in the AWS offerings, you might need to upgrade to the latest version before you can actually flip that switch and use the ARM Graviton option. So for example, if you're using a managed MySQL instance, they only offer Graviton on MySQL 8. You can't use MySQL 5.7. In terms of running your own applications, this kind of depends. Or if you're going to run an open source application, chances are it already runs fine on Linux. And it's already been compiled, if necessary, to run on ARM. Perhaps it's because someone wanted to run it on a Raspberry Pi, but there's also been ARM architectures around for longer than that, and things have been ported to lots of different architectures in the Linux ecosystem. Commercial applications are a bit hit or miss. They may well run on these different platforms, but they may not be supported, so that may be something you need to check on. So for example, if it's based on Java, it will probably run just fine on the ARM version of the JDK, but you may not be supported when you do that. Your own applications, it varies. They may run fine without changes. They may need to be repackaged or recompiled. If you're writing assembler, well, all bets are off. When it comes to different languages, these are probably the easiest ones to migrate. So we've got Java, recent versions of .NET, so that's .NET Core and .NET 5 and 6, and then Node.js. Now, I've been writing Java for longer than 20 years, and I was writing them on Spark workstations and running them on Windows and moving things around. So it's no real surprise that Java runs fine on different architectures. It's also something Microsoft is invested a lot into with .NET. And then Node, well, it's running on your phone. There's tons of JavaScript runs on your phone, so it's no surprise that that virtual machine for Node.js, the V8 machine, runs really well on ARM. Some languages you might need to repackage. Now, a lot of your Python code will run just fine on ARM, but you may find that you have some libraries that are implemented with native code, so when you install that package, it's downloading the binary of that C code, and you actually need to download the right version of that binary. So you may need to repackage it. So if you've got like a zip for a Lambda function that you built on a Windows machine, you may not find that's going to work well on your Linux ARM Lambda function. Same thing may go for Ruby. And then a lot of languages like Go, Rust, C++, and C are going to need to be recompiled. This isn't necessarily a problem. I mean, it's a change to your build process. And languages like Go and Rust have actually made it really easy to cross-compile for other platforms. And you can do that with C and C++ as well. It's just traditionally not quite as friendly to do. Now, a lot of us are running Docker containers, and one of the big things you say about Docker containers is, yeah, Docker containers are really portable. Well, yes, but in fact, they're not architecture portable. They're portable between different machines, but they are architecture specific. So if you want to run your Java application in a container, that Java code of yours may be sort of architecture independent. You could take that same jar file and run it on whichever architecture, but it's running inside a container with a JDK that was compiled to run on x86 64 rather than ARM 64. So you need the right container for the right platform. So what this means is you've got to start with a base image that supports either the right architecture or both architectures, in fact. So if you're starting with, say, Debian or Ubuntu, those are available in a whole range of different architectures, so you can build for whatever architecture you want. If you're starting with some third-party Docker image and then building on top of that, you may find that they only offer an x86 64 version of that container, so you may need to recreate what they did in their steps to create their container, where they probably started with a base Debian container or something similar in order to create your container. There are options where you can build for multiple architectures. For example, you can use Docker BuildX, and that will spit out multiple versions, and you can push these all up together. And then there is a manifest format which allows clients of your Docker container, when they pull, they say which architecture they're going to run, and if you've got a copy for both architectures, it's going to pull the right one down. And that depends on container registry support for those multi-architecture manifests. So that's all kind of the theoretical stuff. What about actually using this? So in my work at clients, I've actually done a couple of different migrations of code in AWS running from Intel to these ARM architectures. So I'm going to talk briefly about those. The first one's Nginx. So that's a pretty straightforward open source product, runs well on different architectures. Now the reality is here, though, tech debt is still tech debt when it's in the cloud. You may think of the cloud as being very new, everything's fresh and shiny, but the reality is we've had the cloud around for quite a few years now. Some of the things I've worked on are now 5, 6 years old, and that means over time they need to evolve, they need to be updated. So sometimes you'll find, yes, it may be really easy to switch to Graviton in AWS, but in doing so, you may realize you've actually got a bunch of other work that you need to do to update things. In this case, it's a very simple architecture. This is both the architecture before and after. It's just an EC2 and an auto-scaling group behind a load balancer talking to other load balancers. So there's a bunch of changes here, only one of which is really related to switching to Graviton. So we're going different versions of Hamilton Linux. We're building different AMIs for the two different architectures. We're going from something called OpenResty that you've probably never heard of to vanilla Nginx. We were using OpenResty because it had Nginx with baked-in Lua support, and you really don't want to know the details about that. it was all provisioned via Chef, and now it's provisioned via Sync, and Sync is not Chef, which is what Sync stands for. It makes use of the instance metadata service v2 instead of v1, and that's a security improvement. And as I said, it's now migrated over the architectures. Now, the biggest challenge out of all of this was this. I'd managed to upgrade everything, or I thought I had. I'd updated my Chef recipes. I'd updated my Packer image. I went to provision one of these instances, and it told me that I hadn't supplied the Chef license flag. Well, as part of my due diligence in upgrading this, I'd gone through and I'd taken all the libraries and tools that we were using and updated them to recent versions. So I'd picked a newer version of Chef, picked the RPM for that, and downloaded and installed that. So it turns out, and I hadn't realized, that Chef is no longer free for commercial use, or they're pre-built binaries, and that's been since April 2019, so you can tell how long it is since this instance had really been updated. And that's why we started using Sync, which is a repackaging of the open source code of Chef with all of the trademarks and other things removed, and supposedly it's all cleared with the lawyers and it's fine to use for commercial use without paying for a license, which is great because it does exactly the same thing, but you have to hunt around a bit for it. Honestly, that was by far and away the hardest part of this whole process. In terms of actually using those Graviton 2 images, it was really a case of, well, I need a different base AMI for Amazon Linux 2. I install a different version of the packages if I'm specifically listing RPMs instead of getting them from a package manager, and there is no step 3. And once I got past that Chef problem, everything worked just fine, and this is currently in production. Now, I also migrated some Java Lambda functions. In this case, I changed the architecture in a CloudFormation template. It didn't have one before because architecture wasn't even an option until recently, and it just defaults to x86-64. I updated the CloudFormation stack, and there was no step 3. I was done. This isn't strictly true because at the same time I was trying to do some stuff with provision concurrency, and that caused all kinds of problems with CloudFormation, but it had nothing to do with the architecture switch. So now I'm going to bravely attempt some demos. And I say bravely attempt because I'm tethered to my phone and I have no idea what kind of network capabilities I have. So let's give this a go. So the first is an example of how easy it is to switch over things in a Lambda function. And what I'm going to do is I'm going to initially spin this up, and this is really brave of me. I'm going to spin this up to run on Intel, and then I'm going to make use of a feature within AWS where it leverages code deploy to migrate over from, that was suspiciously fast. Oh, I missed a flag. That's why it's fast. It didn't actually do anything. It's going to use code deploy to do a gradual switch, 10% at a time, over to the new architecture. So while that's actually standing up, so this time it's actually running, and it will take perhaps a minute, we're going to briefly look at what the CloudFormation looks like for this. Really, the key thing here is just this architecture value. I've got 2 allowed values. I'm going to start off with x86 and then switch to ARM64. And I'm just specifying that on the serverless function. If you're using AWS, you may be familiar with the serverless application model. This is using SAM to deploy these Lambda functions. It makes everything a bit easier. And then I'm just saying the architecture on the resource. And I'm going to flip that value. And along with this deployment preference option, that's what hooks in code deploy. It's going to do that automatic deployment when I change the architecture. Other than that, I've got a very simple Python function. And really, this Python function is just enough for it to return the information to prove which architecture it's running on. So that's actually given me an endpoint. I'm going to copy that. And then in this other terminal. And of course, I left off the extension. So what we see here is that it's telling me it's x86-64, which is exactly what I expect. So what I'm now going to do is I'm going to do a change here, and instead of Intel, I'm going to say ARM. Now this is all making use of a wrapper for CloudFormation. It's an open source project that I actually developed called Stack Manager. It's just really feeding in that parameter value. So I've got a config file, and one version of it's called Intel, and it passes in x86-64, and the other version is called ARM and passes in ARM64. So that should have now triggered code deploy to start switching things over. So it's executing that change set, and it actually won't finish for 10 minutes. We're not going to stand here and wait 10 minutes to watch that. But what we should see is that shortly in our responses, we should start to see 1 in 10 will come back saying it's ARM64. So we will just wait until that happens, which should hopefully be shortly. Now this is running much slower than it would normally do because it's going by my phone, and this would normally be bang, 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 bang. But there we go. There's an ARM64 example. So I would show you what it looks like in the AWS console, but the connection's so slow I can't actually show you the console. It doesn't load. But this will gradually migrate over, and then at the end of it, everything's going to run on ARM. And you can see I ran exactly the same Python code. And that would be the same if I was running Node, if I had a zip file of Java code or .NET Core. Again, it would just be as simple as swapping that flag between the two. And this ability to, what it's doing here is it's running 2 versions of the Lambda function, and it's got weighting between them, and it's migrating that over. Now, you don't have to do it in this sort of increments that automatically move forward. If you wanted to try out ARM, you could just switch 10% of your traffic to the ARM version and leave it like that for a week, and then at the end of the time, just check, did I get more errors on that version than on my regular version? If not, you're probably good to go, and you can look at performance and things like that. Now I have another demo. I'm not going to spin it up because I've already spun it up because it takes a while. And this is more to do with Docker. So what I am going to show you, though, is a Docker build. Let's just... So here's one I made earlier. I've already pushed this up, but we'll just see it doing the Docker build. So it's using Docker build X, and it's going to push this to Amazon ECR, their container registry. So it's already pre-built it. It's got it cached locally. It should hopefully be quick to do and not actually find that it's got to push up hundreds of megs over my phone. It's probably going to run slower than normally. But essentially what this is doing is in parallel, it's building both a ARM64 and an x86-64 version of the same container on my laptop. And it's doing that using, I think, QEMU or something, some library that allows it as a compatibility shim to be able to build that ARM code locally. So you can see kind of here, I've got ARM64 and AMD64, and that's succeeded, and that's tried to push and realized it's already up to date. Now this is deployed on an ECS cluster, that's Elastic Container Service in AWS, and this is set up in a rather strange way to deliberately show a point here. And what it's got is we've got an ECS cluster, and it's got 2 EC2 instances registered with it. One is ARM, and one is Intel. And then I've told it to run a service and run 2 copies and spread them out over availability zones. And that means that one's going to end up on the Intel instance, and one's going to run up on the ARM instance. And perhaps the most significant part of this is in my service definition, which is somewhere here. I am just telling it to pull Graviton latest. There is nothing in that service definition anywhere that specifies an architecture. So I'm making use of the fact that I pushed up both versions of it with the same tag, and that ECR supports this metadata so that it can pick which one it needs to run. So I've already got this running, and there's a load balancer for that. I'm going to kill this off, and let's go to the browser briefly. You can see timeouts and so on. But this is that URL. And all I did in the container build, it's a very simple Docker file. I basically baked in the result of uname minus A into this so that it could tell you what the architecture is. And you should, I know that's a bit small, but still. Basically, it'll tell you whether it's x86-64 or whether it's ARC-64. So we got x86-64, and you can say, just we'll flip between those periodically. So exactly the same Docker file, 2 builds of it for 2 different architectures, deployed to the same cluster. And if my cluster had had 2 Intel instances, it would have always picked the Intel version of the container. If it had 2 ARM copies, it would always pick the ARM copy. So I think that's kind of neat, and it shows how you can gradually migrate things over between the architectures and do sort of try things out before fully committing to switching your architecture. Okay, that's kind of it for, oh, that's the wrong screen. Oh, that's still the wrong screen. There we go. So finally, kind of summing that up, and I know this has gone quicker than I thought it would. Really, a lot of this, the case for using ARM is that total cost of ownership improvement. You're getting better performance for less money. Now, like I said in the introduction, I personally, most of the time it's my client's money. And yes, I have a responsibility to spend less of my client's money, but I also think it's kind of neat running on an entirely different architecture. That's just interesting to me because Intel has been so dominant in the data center world, that architecture, to see something else coming in as an alternative, I think is really exciting. And I think it's going to enable like cheaper computing and some various benefits in the cloud environments. It's really easy to switch certain things. At this point, if you go into AWS and you spin up a managed MySQL instance, it is going to automatically pre-select Graviton, which is ARM, as the instance type for it to run on. Now this is interesting because it's 2 things. One, it means they've got confidence that that's going to perform well enough for you not to know the difference from Intel. And in fact, they say it should perform better. It also means they've got a large amount of these CPUs installed in their data center. This isn't just a niche thing where they've got a few of them off in the corner of the data center. No, they've got tons of these things in their data centers already, so they've really heavily invested in rolling this out, and they are trying to encourage people to migrate over to it. And that's because those server density and things like that I mentioned earlier. Many of your applications can run without change. So it can be a fairly low-risk change. I mean, obviously, you want to take into account performance testing and all those kind of things before you make a switch. You know, for the things that I've switched, they've been fairly low risk. An Nginx server, well, that's going to run pretty well anywhere because it's mostly I/O bound. It's just making calls, proxies off to elsewhere. So that's fairly low risk. And the Lambda functions I moved, I tested them, but they're also fairly low volume. So if you're doing anything significant, performance is going to vary based upon exactly which instructions are being run. Now, for example, with Graviton 3, they tout that there's much greater floating point performance. So if that's part of your use case, you may want to wait till Graviton 3 is more widely launched. Now, it's interesting to see all of Microsoft's investment in ARM, because if you look at the release notes for .NET 5, .NET 6, there's an awful lot of lines of text talking about how they've optimized the CLR to run well on that platform. And that was interesting because at that point, there was nothing you could run that on in Azure, but now there is. So I expect to see that offering increase in Azure over time, and Microsoft's obviously made a big investment into that. And then for AWS, they're really big into custom silicon now. So in addition to Graviton, which is much more general purpose, they've been building Inferentia and Trainium, which are the 2 sides of machine learning. So Inferentia, that's for your sort of Alexa devices, decoding speech and things like that. And then Trainium for low-cost training of where you might have previously used a GPU, you might be able to use a Trainium architecture instead. And then they use this thing called a Nitro system, which is kind of a sidecar for their VM management. So all of these modern architectures, it's how they were able to take a Mac Mini, for example, and plug it into the AWS data center and offer Mac devices, was because they could use the Nitro system as the interface to their block storage and networking and all the other parts of this. And they're able to take basically all of that workload of running VMs off the instance itself, and so you get the full compute power of the underlying hardware, and you're not sort of losing 5% or so to the virtual machine management. So that was it for the presentation, which isn't too bad considering I only found out I was speaking on Tuesday. So any questions? Okay, so the question is really, why has it taken so long for ARM to take off in this server and desktop land? Honestly, I don't know the full story there. It's certainly not the first time that people have tried to do ARM in the data center. There have been various initiatives, including by companies like AMD, where they've tried to create ARM processors and sell them to the data center. But typically the designs have been lower performance. So they've been like those Graviton 1 instances. They've not been quite competitive with Intel and AMD offerings. So I think that's the real differentiator, that finally people have concentrated on creating designs that are more custom made for server workloads instead of adopting lower power designs that were initially made for running in phones and smaller devices. So I think some of it may just be ARM holdings themselves actually focusing on this area rather than people taking existing designs that really weren't meant for that sort of workload. Anyone else?
Do you eventually think we'll start to see more enterprises and other type of companies start to adopt ARM hardware for even on-prem deployments if they're not ready for the cloud and vice versa?
Okay. So the question is whether I expect to see enterprises adopting ARM for data centers on-prem and other use cases like that. I think that's a tough one. Part of it is at the moment, like you take the chips that AWS is using. They're the only ones who have access to it. So that's something, they bought the company. They're the sole consumer of Graviton processors. Now you may be able to go out to Ampere and say, I want to commission a server using some of your CPUs that are being used in Azure and Oracle Cloud, but I don't know how readily those are available and whether all of the available devices, especially with the current chip shortages, are being consumed by those cloud providers. And then, of course, once you're talking on-prem, you've got the regular refresh cycles, and people are very conservative about that. It's easy for us to experiment in the cloud with a different architecture. It's a lot harder for you to make a decision. In my data center, I'm going to start switching over hardware, because if it doesn't work out, that's an expensive investment. Now, I think it will be interesting to see, whether we start seeing more ARM CPUs in laptops and similar devices that people use. Obviously, there's Chromebooks and devices like that have been quite popular. But it's always there, the application problem. There's so many applications built to run, especially in the Windows ecosystem, on the sort of Win32 APIs that are not available. And they're doing more work in that area, and clearly Apple's done a huge amount of work to be able to transition. So I think that's the biggest thing, that increasingly a lot of people are now running Apples that are running an entirely different architecture. And on a day-to-day basis, that may not be something you even notice you're doing. Okay. Any other questions either here or in Slack?
How do you see organizations in the cloud that are using the cloud getting from Intel-based workloads to ARM? What does that kind of transition process look like in your experience?
So the question is, what do I see the transition process being from, say, Intel to ARM in the cloud for enterprises? honestly, it's got to be driven by someone who's, perhaps looking at cost. That's going to be a big driver, and perhaps as part of a regular upgrade cycle. So one interesting thing, we're an AWS partner, and sometimes we get sort of a bit of inside knowledge of things that AWS wants people to do. And one of the things they've told us is they really want people to upgrade off old instance types. So if you're running M4 instances, because the way they label them, M classes are sort of general purpose, and they started with M1, and they're now up to like M6, I think. So if you're running an M3 or an M4, that means you're running that on an older Intel CPU. And they want to decommission those older servers and move things to new ones. So AWS will encourage people to upgrade from older instance types to newer instance types. One of the ways they do that is they typically price those newer instance types that are often a bit faster. They'll price them a little lower. And also Graviton's priced lower. I mean, it costs them less to run because they're the supplier of the CPUs to themselves and they use less power. But it's partly, they're going to say, well, this is faster, plus it costs you less. Why don't you upgrade? And over time, as they launch new regions, for example, you may find you can't get an M3 anymore, and that's certainly the case in a region like Ohio, which is fairly new. You can't get those really old instance types. But they will constantly sort of nudge some of their enterprise customers and say, well, really, you could get some benefits by upgrading. And I think they're going to start more in future nudging people and say, well, why don't you try Graviton? And they've had things like a Graviton challenge where they encourage teams and will sort of give extra help to try and help people move sort of pilot applications across. But a lot of it's going to have to come from those teams where someone's looking at this, well, this is going to save us money. It's going to cut down on our AWS bill, potentially improve performance. Now, I've been partly doing it because, again, I think it's neat, but that's not really the driver for most enterprises. I think that total cost of ownership is really going to be the big driver. Question in the back? Okay, so the question is about RISC-V. So this is another sort of architecture, and I think it has the advantage of being fully open, is that right? So Intel's been looking at developing CPUs in that area. I don't know. I mean, I think the big question there is how widely supported that's going to be for applications. I don't know. There's obviously compilers that will compile down to that. Like anything in the open source ecosystem, people are already building for these different platforms. But the bigger challenge is there a well-tuned Java VM, .NET CLR, things like that? And until those are available, there's never going to be a wide-scale adoption. And there's a bit of a chicken and the egg thing. There's got to be a competitive chip there in the market, and there's got to be ways you can run your application on that. And I honestly think the Raspberry Pi has done a great job for ARM, and it's made people a lot more comfortable in using ARM as an architecture and running applications, especially on Linux, that I'm not sure RISC-V has got any of that sort of flow that ARM has at the moment. But I do think there's a possibility in the future. Yeah. In smaller power devices like microcontrollers, there's definitely a big market for that, but I think it's a while before that might transition into cloud deployments and enterprise deployments. The comment there is just, because it's all open, you can potentially adjust things a lot faster than these commercial and sort of ARM's sort of secret sources to exactly what's in their microprocessors and designs. Okay. I don't see any more hands up, so thank you, everyone.